Hi, in this video, I'll be going through Cardinality of Sets. In the previous video, we have built up our foundations from logic to proving techniques to set theory, and then we use set theory to build our foundations in functions and relations. And then now we move on to using functions to prove things about sets. So what do we mean when we say two sets are equal in sizes, or when they have the same cardinality? Another term for this is x and y are equinumerous. Formally, it means that there exists a bijection between the two sets. And so if you think in the finite cases, if there's a bijection, each element from A is mapped to a unique element in B, and vice versa. And so you could say that they have the same size, or they have the same number of elements. If there does not exist a bijection in these two cases here, for example, if it's not injective, then there'll be more elements in A, because there'll be elements in A that has to be mapped to the same element in B. And if it's not onto, then there are elements in B not mapped by any element in A. And so you can see how by defining it to have a bijection is the most intuitive and consistent way with our understanding of sets, even in the infinite case. So let's see some properties about equinumerity. Well, x is of course equinumerous to itself. If x is equinumerous to y, there exists a bijection from x to y, but that also means there exists a bijection from y to x. Just take the inverse of f. And so y is also equinumerous to x. And if x has a bijection with y, and y has a bijection with z, by taking the composition, you get that x has a bijection with z. And so x is equinumerous to z. And if you recall our chapter on relations, this is known as reflexive, symmetric, and transitive. And so you can actually form an equivalence relation using the equinumerity symbol. Now, let's prove something when two sets are equinumerous to each other. And these two sets are very commonly used. They are the natural numbers and the integers. While it seems like the integers have double the amount of the natural numbers because it has both positive and negative, they're actually equal in sizes because you can just extend them to infinity, and every element in n can be mapped to a specific element in z. So you can define the function as the following. If n is even, you divide it by 2. And if it's n is odd, you minus 1, you divide it by 2, then you take the negative of it. The picture is over here. So you can see 1 will be mapped to 0 first. And then continuing, all the even numbers will be mapped to a positive integer. And all the odd numbers will then be mapped to a negative integer. It might seem counterintuitive, but it actually works out to be a bijection, and this proves by definition that n and z are equinumerous in sizes. So, let's first check that f is injective. We have already done so multiple times when doing functions in previous videos, but we have to run it through again to refresh our memory. So we take two objects in n, and they have the same output. Because they have the same output, they must have the same parity. Because if n is odd and x2 is even, then this will be negative and this will be positive. And so that can't be happening. Hence, we know that either they are both even or they are both odd. If they are both even, that means they fall into this function. And so x1 equals to x2. If they are both odd, they again fall into this function, and so x1 equals to x2 again. Hence, f is injective. Now we need to check that f is surjective. So for any integer greater than 1, you can just take f to be 2n, which equals to 2n over 2, which equals to n. And this will be a natural number. Now, if n is less than 0, then f of minus 2n plus 1 will equals to n by a function defined. And minus 2n plus 1 is also a natural number. So, either cases, there will always exist a natural number such that fx equals to n. You can look through the proof again, but it should be fairly simple for this case. And this proves that the natural numbers and z have the same cardinality. Now, we can define when sets are finite and when sets are infinite. Of course, we want them to be consistent with our idea, where finite sets are sets that you can explicitly list out. And so, it means that X is either an empty set or it is in bijection with a set that you can explicitly list out. This set that you explicitly list out is known as the reference set, or you can just notationally write it as NN. It's just writing the set with 1 to n elements. And so if it's finite, it's either empty or there's a bijection with this NN. And it's infinite if it's not finite, meaning for all n, and all maps, f is null, is not a bijection. And so, while we make this definition of finite infinite, it still does not prove why n, the natural numbers or any set is infinite. Of course, we already proved certain sets are finite, such as the empty set and the reference set, but we have not proved any sets is infinite. And so, let's say we want to show that our understanding of the natural numbers is infinite, is correct. It means we cannot find a bijection with any reference set. And that's where this principle comes in. For any n, there does not exist a bijection from nn to a proper subset of itself. And this is known as the pigeonhole principle that you have learned in counting. The proof of this takes a bit of a more difficult approach because the function that you need to define needs to be defined recursively. But you can read online or in the book for ideas of how to define the function. But the main idea will be just to think of it as the pigeonhole principle, and if you have more elements in one set than the other, then of course you can't map all the elements unique to a one output by itself, and two elements must be mapped to the same output. And so if you apply this to the natural numbers, it says that if this was n, or then you can just, and if there exists a bijection, then you can flip it around and n will go into nn, and this will contradict the pigeonhole principle. Or another way you can put it is also because of this proposition, it shows that the cardinality of a set is well defined. Because you cannot have two reference sets that have different cardinality for the same set that you want. So x, if the cardinal of x is n, it means there's a bijection with nn, and this is the only reference set that it has a bijection to. or else it will contradict the pigeonhole principle. Also, if you know that A is finite, it will never be equinumerous to any of a proper subset of itself. Because if A equals to n and there's a proper subset meaning m, let's say this will be strictly less than n, it cannot have a bijection with any of the reference sets m. And so if A is finite, A cannot be equinumerous to any of the proper subset of itself. However, you can see if you take the negation of this, it means that if you take the contrapositive, if A is equinumerous to anything, there is a proper subset of A, then A must be infinite. And this is just a contrapositive to this. And you can also just use this to prove why the natural numbers is infinite. Because the natural numbers, you can just form a natural bijection with the even natural numbers. And so this will obviously be a proper subset of n, but they are equinumerous, and so n is infinite. Hence, we have now constructed an infinite set. And we'll be moving on to prove more when objects are countable and why are it's uncountable, and we'll build our foundations from there. Thank you for listening. I've come to the end of this video. I hope you have enjoyed it. See you in the next one.